All right, welcome back. Let's get started. So, in the last lecture we looked at the number states. In this lecture, I want to talk about, I want to complete the description by relating the quadratures we talked about with the operators, okay, and how this can help us derive the uncertainty relation for the quadratures, okay. So, these are some definitions that we have already seen. So initially when we talked about the squeeze states, we introduced this idea of quadrature x1 and x2. And then we said this quadrature essentially are related to the electric fields. And then in turn, they can be related to the position and momentum of the harmonic oscillator, right? And then after that, in last weekend, we introduced this lowering and the raising operators. They seem like different ideas altogether, right? So, but internally they are related to each other, and we'll show that now. Okay. So how do I convert this quadrature that I defined in terms of fields and this Q? How do I convert it in operator? Well, we know what's an operator for Q and P, isn't it? X. So basically you have a canonically conjugate variables. So wherever I have, the classical expressions, I'll simply put a cap on it. I'll call it an operator. Okay. So what I'm going to do is here, I'll say my X cap is my operator for this one. X1 is simply going to be dependent on the Q cap. Q cap is basically, Q is, we know that it is square root of M times X cap. Similarly, X2 is going to be related to the momentum operator. Okay. Now I want to find out what is the relation between X and the raising and lowering operators. To do that, we will start with this expression on the right, A dagger in A. Let's try to find out what is the expression for X and Px operators in terms of the raising and lowering operators. Okay, so then we can substitute. So what we'll do first is, let's do A, I'm dropping the hats, okay, these are operators anyway, we understand. A dagger, A plus A dagger is going to be 1 by square root of 2m h cross omega. And then, so the Px terms will cancel. So what you'll be left with is 2m omega x cap. All right. So this is basically the 2m omega will go out. So the square root 2m omega by h bar into x cap. Okay. If I change I'll take the left and right, I'll write x cap. My x cap is going to be square root of h cross by 2m omega into A plus A dagger. All right. Algebra, nothing much. No rocket science. Okay. So A minus A dagger now, I'll try to find out because I want to get an expression for the momentum operator P. So for that, what I'll do is A minus A dagger. So basically, I'll have same 1 over square root of 2m h cross omega into now the x expressions will cancel because we are taking a negative. So essentially you'll be left with 2i px cap, correct? So 2 will go out. So I'll be left with I square root of 2 by m h cross omega into p cap or px cap, whatever. That implies my p cap or px cap is going to be, it will go the other side, and this will be a minus I times m h cross omega by 2 into A minus A dagger. All right. So now what I will do is, I will try to find out what is x1 operator, quadrature operator. Okay. Previously we said it's a field, right? Now in terms of operator representation, what is it? Okay. So if I take that, I'll take x1 hat is going to, okay, so because I have in terms of x, q we said is square root of m times x cap. So I'll absorb that square root of m and then m omega divided by 2h bar whole thing under root into this expression here for x cap. So this will be square root of h cross omega by 2m omega, sorry, h cross by 2m omega into a plus a dagger. What will that be? Well, square roots, so h cross goes, m goes, omega goes, and square root of 2 into square, whatever, denominator you have 2 square roots of 2, so this will be equal to half of a plus a dagger. Your quadrature is simply a sum of, x1 is simply a sum of raising and lowering operators, average of raising and lowering, x1 quadrature. Similarly, x2 quadrature is going to be equal to, now there will be an additional, p will be equal to what? In terms of the generalized, this is a generalized coordinated representation, right? So here my p is going to be px by root m. Okay. So that's why we'll bring that in to this. So this will be 1 by 2m h cross omega whole thing under root into minus I times 2, by m h cross omega by 2 into a minus a dagger. Again, m, h and h cross and omega will go out. So we'll be left with minus I by 2 a minus a dagger. This is my quadrature, x2, operator for quadrature x2. Now the question is, once you know the states, you can again compute, like what we said, the interrelation, right? So we will use this to just compute the uncertainty relation for x1 and x2. Now, this is an exercise problem from Mark Fox. So this is, you can go to chapter 8, 8.1 is this. So the question is basically to evaluate the commutator x1 hat, x2 hat. Okay. Previously we did a dagger, that was 1. But now x1 hat and x2 hat, what is it? Commutator bracket. So to do that, I'll say x1 hat, I should actually, x1 hat, okay, my usual laziness, I'll drop hats, x1 comma x2 is going to be equal to x1 x2 minus x2 x1. Do they commute? Well, most likely they will not. Okay, of course they will not, because we know that there's an uncertainty relation between them, so they will not. Okay, so what is x1 x2? x1 x2 equal to, x1 was half a plus a dagger, x2 was minus I by 2 a minus a dagger, so minus I by 4 a plus a dagger into a minus a dagger, and that will be equal to, well, I'll do one thing, I want to conserve space, so I'll move this on the top. This is what I need to evaluate, so I'll put this on the top here. Okay, so now this is equal to minus I by 4 a times a operating on a, okay, a square essentially, okay, plus a dagger, minus a dagger plus a dagger a minus a dagger. This is my x1 x2. Similarly, I can calculate what is my x2 x1. That's again minus I by 4 a minus, okay, since I'm on this space saving spree, let me push this. Okay, a minus a dagger, wait, yes, into a plus a dagger, that's going to be minus I by 4 a minus plus a dagger, a dagger minus a dagger a plus, wait a minute, a dagger minus a dagger a minus a dagger a. Okay, this is going to be again another minus. This is minus a dagger. right? This is what it is. So if I compute x1 minus x2, rather, the commutator bracket, x1 comma x2 is going to be difference of these two terms, expressions. So basically your AA and A dagger A will cancel out because there's a minus, right? Both have a minus I by 4. So what it will turn out is minus I by 4 bracket let me take out a minus sign out. So I'll simply write it as I by 4 into, if I take the minus inside, rather, A dagger minus A dagger A. This is from the first term, x1, x2. Minus, again we are taking the minus inside and we are doing a minus. So minus minus, again one more minus. So A dagger plus only it will become A dagger minus A dagger A. So this is going to be I by 2 times, surprise, A dagger minus A dagger A. That's going to be equal to 1. So this is going to be equal to I by 2. Okay. So the commutator bracket between x1 and x2 is going to be I by 2. Now, how do I get the uncertainty product? So I'm going to pull a rabbit out of the hat and I'll say that, you can show, okay, some very basic theorems in statistics. You can actually look at how the variances behave and how they're related to the commutator bracket. We are not proving it. We are just giving you this expression. What basic analysis, statistical analysis will tell you is that, or delta x1, so let's say you have two operators, A and B, A square times B square, variance of A square into variance of B square is always going to be greater than or equal to the commutator bracket between the two whole square divided by 4. If I apply this to my context here, I have delta x1 whole square, delta x2 whole square is greater than or equal to, what is the commutator bracket between x1 and x2? I by 2. So I by 2 will become 1/4. 1/4 into 1/4. So that's greater than or equal to 1 by 16. So I can say that delta x1, delta x2 should be greater than or equal to 1 by 4. This is my uncertainty relation for x1 and x2 quadratures. All right. So effectively, of course, I didn't prove it all the way. We just took one result, standard result, and then we showed it. In fact, you can actually, it's just, we'll have to close this course soon. So we're not going, but I think you can show it. There are many, many different places this is done. Okay. In fact, the variance, they'll actually take the expectation value whole square, square of the expectation value, and then minus expectation value whole square. That will be the variance. And you can go step by step and what is expectation value of the square of this. It becomes a little tedious for us to do, but we can show that this is definitely greater than, the expectation value squared. Okay. So that's how we can relate. So you see, we initially assumed that this was the truth, but now we are getting to the same numbers. Okay. That's how all this ties up. So I have just one more thing to go. We will just talk about what is coherent state. Once we do that, we will simply go into some applications. Okay. With that, we'll close the course. So yeah, thank you very much for your attention. Any questions? All right. Okay, then we'll stop here.